Welcome everyone to today's TSVP talk. Thanks for joining on an unusual Wednesday instead of the usual Thursday time slot. Jon Brundan is visiting us from the University of Oregon. He'll be around for all of March, April, and May, essentially. Jon obtained his PhD at Imperial College. Subsequently had a research position at the University of Cambridge, and since 1997 has been based at the University of Oregon as a faculty member and has been a full professor there since 2008. Among other things, he has been a plenary speaker at an AMS meeting. He's a fellow of the American Mathematical Society and has been an invited speaker at the International Congress of Mathematicians in 2014 in Korea. About 80 odd papers, including some in top journals, over 2,500 citations on MathSciNet, and almost a dozen, let's say, editorial responsibilities. So very involved in the mathematical community on kind of every aspect, a bunch of PhD students, countless accolades all over the board. So please let's welcome Jon, who's going to tell us about the Heisenberg category today.
Thank you, Leron. It's a pleasure to be here, and thank you all for coming on this Wednesday. So I think giving a math talk to an audience who aren't trained algebraists necessarily is a bit of a challenge. So I'm going to give it a go, and we'll see how it goes. I might do a useless job. I'm apologizing in advance if I do, but I want to try and give you kind of the flavor of the sort of technology that I'm using, which is kind of very kind of diagrammatical, very graphical in what's going on, even though we're trying to do some higher category theory. So it's kind of a challenge to communicate that at the same time as giving you a flavor of actually how in many ways it's easier than the algebra we used to do. So let's see if we can get that. See, yep, that looks good. And the lights are dim, so hopefully you can all see that. So let's start at the beginning. I want to kind of tell you this story. I gave this bold title, the Heisenberg category. So we should start off with the Heisenberg group. That's the closest I think I come to Heisenberg himself in the talk. But the Heisenberg group, I think that as a mathematician, the first time you see the Heisenberg group, it's when somebody is trying to give you an example of a group that is some sort of continuous group, some sort of Lie group. So it's a group of matrices with entries in the real numbers where the multiplication is not commutative. And it's maybe the simplest example. There it is, the Heisenberg group. It's that group of upper triangular 3 by 3 real matrices under matrix multiplication. I'm not a physicist, so I don't really know why Heisenberg's name got attached to this group, but I imagined it was in the 1930s, and he was just starting to kind of get this idea of non-commutativity as sort of being the hallmark of quantum mechanics that he was developing at the time. So I don't know. My interest is very, very different, of course. Mathematicians do that a lot. They take something which has a sensible name in some other part of science, and they kind of steal the name and use it in their own way, which the originators wouldn't recognize. And that might be the case for this talk. So actually, I don't want to look at the Heisenberg group, that group of 3 by 3 real matrices. I want to look at the Heisenberg Lie algebra. So that's just the tangent space to that Lie group at the identity. And it's just a vector space now of 3 by 3 matrices of that special form. So strictly upper triangular matrices. And now it's a Lie algebra, so the operation is the Lie bracket, which is just the Lie bracket xy is just the commutator xy minus yx of those matrices. And now it's linear, so it's a vector space, so I can give you a basis for this 3-dimensional real vector space. And the standard basis is P, which is that matrix unit. P star, I have slightly weird notation that will become clear in a second. P star is that matrix unit, and then Z is the matrix unit with a 1 in the top right corner. So of course, these 3 matrices span that Heisenberg Lie algebra, that 3-dimensional real vector space. And to work out the multiplication, you just need the structure constants for the Lie bracket. And it's extremely easy. The Lie bracket of P and P star, so if you take the commutator of these two matrices, you get Z. Whereas the element Z actually commutes with everything. So Z is in the center of this Lie algebra. So this right here, this is a complete set of multiplication rules in this Lie algebra. P star is Z, and Z commutes with P, and Z commutes with P star. Those commutators are zero. You can generalize a little bit, right? I was just putting A and C, and I had just a zero in my 3x3 matrix before, but you can grow that A to being some row vector in Rn, and you can grow that C to being some column vector in Rn, and then this single zero in the three-dimensional Heisenberg Lie algebra will become some n by n matrix of zeros in its own right. So here's the kind of the next one up. So this is a 5-dimensional real vector space, and here's the basis, P1. And looks like I got that one wrong. Let's fix that one. P1 star is meant to be, okay, so that's meant to be P2 star, and that's meant to be Q1. What am I doing? I'm doing it all wrong now. There we go. P2 and P2 star is meant to be this guy. Sorry. P1 star. Let's fix it so that we have it right the next time we do this. Something like that, right? And it's almost right. It's not quite, but hey, good enough. So I'm trying to just write down the standard row vector guys in P1 and P2, and the standard column vectors in P1 star and P2 star. And Z is as it was before, is that one in the top right corner. So this is now a 5-dimensional real vector space. And the Lie bracket, well, the PIs commute with themselves. PI, PJ, that bracket is zero. The PI stars commute with themselves. Z is central. But if you take the commutator of a PI with a PJ star, well, you get zero if I is different from J. You get Z if I equals J. Right? So that's just the next Heisenberg Lie algebra up there. And actually what I want, I don't want the 3-dimensional, the 5-dimensional, the 7-dimensional. I want the infinite dimensional Heisenberg Lie algebra, where I just carry on this pattern. So now it's going to be an infinite dimensional real vector space. And the basis is just the P's, P1, P2, P3 forever. And the P stars, P1 star, P2 star, P3 star forever. And then this element Z, which is going to be central. And the commutator relation is telling you the Lie bracket. The PIs commute with themselves, that Lie bracket zero. The PI stars commute with themselves. But if you bracket a PI with a PJ star, you get, well, before I had delta IJ, Kronecker delta Z, and I've snuck in a little normalization, an extra scale factor of I there. I always use the letter I, and if you work over the complex numbers, and are used to the letter I being the square root of -1, you're out of luck with me. So this I is just the positive integer 1, 2, 3, 4, the index of the PI there. So that's the infinite dimensional Heisenberg Lie algebra. So it's still actually, I think it's a pretty boring Lie algebra. Honestly, these are not very interesting Lie algebras. It's not why they're important. For me, the reason this infinite dimensional Heisenberg Lie algebra is interesting is not it's itself, but it's what it acts on. And so I'm going to tell you what this infinite dimensional Heisenberg Lie algebra acts on. What I'm telling you is what's called the basic representation of that infinite dimensional Heisenberg Lie algebra. Some people call that the Fock space representation of this Heisenberg Lie algebra. So this is another infinite dimensional real vector space, and the basis vectors in the Heisenberg Lie algebra are going to act on that other vector space just as linear transformations from that vector space to itself. And those linear operators just need to satisfy those same commutation relations of the generators of the Heisenberg Lie algebra. And what real vector space is it? I call it capital lambda. I'm working over the real numbers at the moment, so it's capital lambda sub R. And it's infinite dimensional vector. In fact, it's an algebra in its own right. Lambda is a polynomial algebra. It's polynomials in these P variables, P1, P2, P3, and so on. So there's infinitely many variables, but its elements are just polynomials in that infinite alphabet. And the coefficients are just real coefficients. And the way the Heisenberg-Lie algebra acts on it, so for each pi, I need to give you a linear map from capital lambda to capital lambda to give you the action of the pi. And pi just acts just by multiplication by pi. That's why that's an algebra. I can multiply by pi, and that gives me a linear map. And the pi star, now you're beginning to see why I call it pi star. The pi star acts as a differential operator. So pi star actually acts, so whereas pi kind of adds to the degree because you're multiplying by pi, pi star is differentiating with respect to pi. In fact, to get my normalization, I snuck in that little normalization. You have to put in an extra normalization there. So pi star, it's differentiate with respect to pi and then multiply by the I, the index in the pi star. So these are linear maps, pi and pi star, from this real vector space to itself. And the point is that they satisfy the Heisenberg relations. And I think at the bottom in yellow there, you could see I just did one little calculation. I calculated the commutator of pi and pi star. And I'm applying that to some polynomial f in lambda. And so the first guys you have, so pi star is this differentiating, and then you multiply by pi. As the other way around, I'm first multiplying by pi, and then I'm differentiating. And so here you have to just use the chain rule to work out that commutator relation. You see things cancel, and you end up at the end with negative I times the polynomial f that you started with. So this is like negative I times the identity function. And the commutator relation for pi and pi star, it was meant to be IZ. Whereas I've got just scalar multiple by minus I. So what this little calculation, it's a silly calculation. It tells you that the central element Z on this basic representation, Z must be acting as -1. So that's what I put in there. Okay, so this is this basic representation of infinite Heisenberg-Lie algebra. Z acts as -1. I say it has central charge -1. So feel free to stop me, but I'm trying to kind of not totally bore people who know this, but to kind of give enough background that you can kind of follow along what story is going on here. So why is it called capital lambda? Well, capital lambda is the traditional symbol used in math to denote the algebra of symmetric functions. So this basic representation of this Heisenberg-Lie algebra is also known as the algebra of symmetric functions. Remember, it was this polynomial algebra generated polynomials in these infinitely many variables, P1, P2, P3, and so on. So I need to just tell you a little bit about symmetric functions. So this was my attempt to give kind of a crash course about symmetric functions. Actually, we're going back several hundred years in time at this point, from I guess Heisenberg 1930s, but we're going back really right back to the time of Newton. Newton was a master of symmetric polynomials. So let me just give a really quick account of symmetric function story. So imagine you have three variables, x1, x2, and x3. Then I would talk about a symmetric polynomial in those three variables. It's just a polynomial in those three variables, which if you flip the variables around, you permute x1, x2, x3, the symmetric polynomial is invariant. It doesn't change. So I've written some examples of symmetric polynomials right here. These are called, this family of examples are called power sums. So the first power sum P1 is just the sum of the three variables. And you can see that's symmetric in x1, x2, x3. The second power sum is the sum of the squares. Third power sum is the sum of the cubes. So that's one basic family of symmetric polynomials. In fact, these P's, they're the same. They're going to be the same as the P's in my infinite dimensional Heisenberg-Lie algebra that I have there. Here's another family of symmetric polynomials that I know everybody's seen. These are called the elementary symmetric polynomials. So E1 is actually the same as P1. It's just the sum of the three variables. And then E2, I've written it here, it's x1, x2 plus x1, x3 plus x2, x3. And you see it's symmetric in those. And E3, that's the product of three of them. So E2 is sort of products of pairs. E3 is products of triples. And if there's only three variables, that's what you get. And I'm just sort of rambling about why you will know symmetric polynomials, but I think maybe even in high school, you probably took a cubic. there's that. So this is three linear factors: t minus x1, t minus x2, t minus x3. And when you multiply out that cubic, you get the actual cubic in the variable t, and the coefficients are exactly these elementary symmetric polynomials. Of course, that's the sort of thing Newton would also have learned in high school. So it's kind of we're on that track. Newton was kind of astonishing. He actually has some identities in the theory of symmetric functions named after him, the Newton identities. It's kind of astonishing that this strange piece of algebra he also had an impact on. So I wrote down the very simplest Newton identities. They relate the power sums to the elementary symmetric polynomial. So P1 is E1, P2 is E1 squared minus 2E2. So if you square that guy and you subtract twice that guy, you'll see indeed you get that second power sum. So this is a Newton identity. And if you rewrite that identity, you see that to get E2 in terms of power sums, you need to put a half in the formula. So you can write the power sums in terms of the elementary symmetric polynomials easily, but to go the other way, to write the elementary symmetric polynomials in the power sums, you need to start dividing by positive integers. There I just need to divide by 2 for the first one. Okay, so now we've got to start sort of taking some bigger steps. So that was my algebra of symmetric functions. That was my basic representation of this infinite Heisenberg Lie algebra. It was polynomials in P1, P2, and so on. There I had infinitely many variables, not just 3 variables. So you've got to go from symmetric polynomials in 3 variables or 4 variables or 5 variables to symmetric polynomials in infinitely many variables, x1, x2, x3, dot, dot. And then the power sums, I mean, the first power sum just becomes the sum of all the variables, and you have to just be a little bit careful to make sense of that infinite sum. It's a standard process. And the second power sum is the sum of all the squares, and so on. And the elementary symmetric polynomials, similarly, they just become infinite sums. E1 is the sum of all the variables, E2 is the sum of all products of pairs, and so on. These power sums and elementary symmetric polynomials, when you go to infinitely many variables, they both give you generators of this polynomial algebra lambda. I originally defined it as polynomials in the power sums, but it can also be defined as polynomials in these elementary symmetric polynomials. It's kind of natural to go up to infinitely many variables. It might seem weird, but somehow you see much better stability going on when you pass to infinitely many variables. Anyway, both the power sums and the elementary symmetric polynomials, they generate this algebra of symmetric functions, our basic representation. For me, I'm a category theorist. I don't work over the real numbers. I want to work over the ring of integers. So that's why there's lambda sub r. Actually, I care about lambda, which isn't going to be polynomials with real coefficients. It's going to be polynomials with integer coefficients. So that's the correct guy I want, capital lambda, the ring of symmetric functions. It's polynomials in these E1, E2, E3, this infinite family of elementary symmetric functions. And now it's important that I told you it was polynomials in the E's, not polynomials in the P's. You can write any P as a polynomial in the E's, you just need integer coefficients, but you can't go the other way around. You can't write E's in terms of P's over the integers. You need to divide by 2 to get that one, right? So and for me, it's very important that I've got to work over Z instead of over R. So it's a slightly weird looking place maybe, but the correct definition of lambda is that it's the ring, a commutative ring freely generated by these elementary symmetric functions, these E's. So this ring of symmetric functions, it's been studied all the way back to Newton's time, but in particular in the mid-19th century, it was sort of one of the kind of favorite topics for people to be thinking about, for mathematicians to be working on. So we're like mid-19th century math here, this kind of thing. So the ring of symmetric functions, capital lambda. So it's it's polynomials with coefficients in Z. So it's not a vector space over R anymore. Instead, it's a module over the ring Z of integers. But it still has a nice basis as a Z module, and this remarkable basis is the basis of Schur functions. So I'm going to not quite tell you very much about Schur functions, but they're a linear basis for this Z module, right? So the EIs, they're generators as a ring where you can multiply. The S lambdas are just a linear basis where you can only take linear combinations of them. So these are the Schur functions. They're indexed by partitions. So S lambda, the lambda of partition. And I've got to kind of quickly tell you what I mean. What's a partition? Here's an example of a partition. 3, 2, 2. That's a partition of the number 7, right? I've just written 7 as a sum of positive integers. And for partitions, you always arrange the parts in weakly decreasing order. When you have a partition like 3, 2, 2, it's quite normal to visualize it by drawing a diagram. So I've drawn here, this is called the Young diagram of the partition 3, 2, 2. It has 3 boxes in the first row, 2 boxes in the next row, and 2 boxes in the next. So for me, I'd always sort of draw Young diagrams in a corner like that. That's what I mean by a partition, lambda. As a partition of 7, interesting to count partitions of big numbers, not so easy to do. These are the guys that label the basis vectors in this amazing basis of the ring of symmetric functions, this basis of Schur functions. And I'm not quite going to tell you what they are, but I'll tell you where they come from, why they're called Schur functions in just a second. This ring, lambda, as is just this Z module with basis, these S lambdas, it has an inner product on it, an integer valued inner product. And it's very simply defined. These Schur functions, these S lambdas, they form an orthonormal basis. So S lambda dot S mu, the integer you get out is 1 or 0 if lambda equals mu or not. So that's this dot, that's the inner product on the ring of symmetric functions. And this is relevant because, well, I already told you about the power sum PR. Multiplication by PR gives a linear map from lambda to lambda. That was my PR operator. Why did I call the other operator PR star? Because it's the adjoint operator with respect to this inner product. That means this formula here. To calculate PR star on an F, if you dot it with any polynomial G, it's the same as F dotted with PR times G. So that's saying that PR star is adjoint to PR. And adjoint is always with respect to this special inner product where the Schur functions are orthonormal. It's a long way I had to go, but I've got to get to this Heisenberg ring. So before I started with the Heisenberg group, then we had the Heisenberg-Lie algebra, which we made infinite dimensional. Now I'm passing to actually the thing I really care about, which is the Heisenberg ring, where it's not a vector space over the real numbers anymore. It's just a ring. So my coefficients are just integers. And I'm just going to call that H. That's going to be the Heisenberg ring. And the Heisenberg ring is going to act on the ring lambda of symmetric functions. In fact, the way I'm going to define the Heisenberg ring is that its elements are just Z linear operators from lambda to lambda, just Z linear maps from lambda to itself. And this is where I had to make this switch from power sums to elementary symmetric functions, because the power sums don't work well over Z. The elementary symmetric functions do. That was that dividing by 2 in Newton's identities. So H is generated by the operators that are given by multiplication by the ERs, and then the adjoint operators, these ER stars, with respect to this inner product. And so these give you linear maps from lambda to lambda, and the ring that those linear maps generate, that's the Heisenberg ring. Okay? And by definition, the Heisenberg ring acts on this ring of symmetric functions. So sorry, that took me kind of a long time to set it up, but this is kind of the magic piece of classical mathematics, really still 19th century mathematics that is kind of important for this story. There's lots of wonderful things. This is sort of a magic pair, this action of H on lambda. So I want to. So this is almost the end of the first half of the talk, where I'm just trying to introduce these very sort of classical objects, this Heisenberg Lie algebra, this Heisenberg ring, acting on the ring of symmetric functions. Let's just play a little bit because I kind of threw loads of stuff at you. For example, here's one of the commutator relations. E1 was the same as P1. Remember P1 and P1 star, that commutator in this action on lambda, that was normally Z, but Z was -1 for that basic representation. So that's kind of the very first basic commutator relation for our Heisenberg ring. And if you work with this basis of Schur functions, these S lambdas, so I just write S and then I draw the Young diagram usually, that's an S lambda. The way E1 acts on S lambda is it acts by adding a box. So you've got to keep this kind of Young diagram shape where you're sort of like Tetris, you're squished up in that corner. Gravity is sort of pushing you up. So the only places you can add boxes keeping that shape in that corner are those three places. And that's exactly how E1 acts. It adds 1, 2, or 3 addable boxes, and you get the sum of those 3 Schur functions. That's the action. And E1 star, the adjoint operator, well, of course, that's the adjoint operator. So it's got to act as in the dual way of adding boxes, which is removing boxes. So for this Young diagram, this partition, there's 2 boxes you can remove to leave another Young diagram. And that's how E1 star acts. It gives you the Schur functions where you remove those 2 boxes. So E1 adds a box, E1 star removes a box. And the commutator here being -1, the reason for that is that if you look at one of these Young diagrams and you look at how many addable boxes there are, there's always 1 more addable box than there are removable boxes. And if you think about it, you'll see that's how you see that this commutator is -1 when you're thinking in terms of these Young diagrams. So at the end here, I drew I started drawing some of the Young diagrams. Remember, these Schur functions, which are the basis of this basic representation of the Heisenberg ring. So that's the empty Young diagram, the partition of 0. That's the only partition of 1. These are the partitions of 2, and then these are the partitions of 3, partitions of 4, and of course, so this is called Young's partition lattice. And of course, it extends up forever. And what you're meant to think about is that this is sort of a picture of a basis of this basic representation. And you're meant to think about the empty Young diagram at the bottom. That's kind of the vacuum vector in this Fock space representation. And the way the E's act, they act by adding boxes, and the E stars remove boxes. So it's sort of you act with E, and you sort of walk up this Young's partition lattice as you act with E. So kind of E is adding energy, and E star is removing energy. And it's not a bad way of thinking about this basic representation. Okay, so that was sort of setting up the groundwork so that we've all got a Heisenberg ring acting on ring of symmetric functions. So now that was sort of easy stuff. And now I've got to make this difficult jump because actually I'm a category theorist as well as a representation theorist. So I've got to make this jump to category theory, which is a little bit of a challenge. In fact, the thing I study is this is the sort of made up word for the day. I study this subject called categorification. So it's kind of the search for higher structure. That's how I like to think about categorification. So I've given my example 0 that I'm about to go through is a kind of very dumb example, but it will give you the idea straight away. Take the natural numbers, the set of natural numbers 0, 1, 2, 3. There it is. That's kind of a basic structure. We're all used to it. And categorifying that structure, this is this red arrow going down with the question mark, because I don't really quite know what categorifying is. But in this case, what you're meant to end up with is vector spaces. So there it is, VEC. VEC is the category of finite dimensional vector spaces. So now I've got my challenge is to teach. Even most mathematicians don't really like category theory that much. So I've got to kind of but all a category like the category of vector spaces, it has objects. In this category, the objects are the finite dimensional vector spaces. And then there are morphisms. There are maps between objects. So categories consist of objects and morphisms with some properties, of course. The objects are the finite dimensional vector spaces, and the morphisms are the linear transformations between vector spaces. So you all probably know that if you have a finite dimensional vector space, you can pick a basis. So it really just depends on the dimension. If you have any two vector spaces of the same dimension, you can write down an isomorphism between those vector spaces, just taking one choice of basis for the first guy to a choice of basis for the second guy. So actually, vector spaces up to isomorphism only depend on their dimension. So this is what this upward arrow here is. So this going up is easy. This is decategorifying. And going from the category of vector spaces back to the natural numbers is just by taking dimension. Take a vector space, an object of this category of vector spaces, take its dimension, it gives you a natural number. And that natural number tells you exactly what vector space you started with, uniquely up to isomorphism. So this taking dimension of a vector space to get a natural number, it's forgetting a lot of the structure of vector spaces. We've forgotten everything about all those linear transformations between those vector spaces and all those ways those vector spaces might have appeared in nature. We've just remembered the dimension, which is really just remembering the isomorphism type of the vector space we started with. So this is the easy direction, decategorification. And categorification is sort of going up from the natural numbers to the category of finite dimensional vector spaces. It's sort of, we've added a whole lot of extra structure to the natural numbers. We've now got vector spaces, we've got linear maps between them, we've got matrices. It's a bit of a silly example of what categorification is, to be honest. But if you've never seen this word, you have to see this example first. You can add two natural numbers together, right? Well, adding natural numbers has a categorical analog. You can take two vector spaces and take their direct sum. And the dimension of that is the sum of the dimensions. And there's also multiplication, because you can take two vector spaces and you can tensor them together. And the dimension of a tensor product is the product of the dimensions. So these categorical operations, direct sum and tensor product, are kind of the categorifications, the higher structure underlying addition and multiplication of natural numbers. It's a very weird way to think, but you've got to get on board just for a second. So when I use this word decategorification, the symbol I use when I'm decategorifying, I write capital K sub 0. And that stands for something called the Grothendieck group, which is kind of a slightly scary construction. But in the case of vector spaces, for example, K0 of the category of vector spaces is just the integers, the ring of integers here. That basically comes down to taking dimension. So in general, K0 of the sort of categories we're going to be looking at, it's forgetting the structure of the morphisms in the category. It's even forgetting the objects. It's remembering the isomorphism type of the objects. And you complete it so that it's actually an abelian group. That's why I'm getting Z here. Whereas in my dimension example, you only got natural numbers. You add minuses as well. So there's this fancy thing called decategorification called K0. So it's just taking an object V of your category, and I just put square brackets around it. It means it's isomorphism class in the Grothendieck group. And the way you add these isomorphism classes, U plus V, it comes from the direct sum operation on the category. So that's kind of how the addition making K0 into an abelian group comes from some structure on the category, this direct sum operation. So it's kind of a hard sell. So actually, it's a little bit better for vector spaces because you don't just have direct sum of vector spaces. We had tensor product of vector spaces. So you can sort of multiply vector spaces by taking tensor product. Vector spaces are what's called a monoidal category, not merely a category, but they have this extra tensor product operation, which is called a monoidal product on here. And when you're taking K0 of a monoidal category, you don't just end up with an abelian group, you end up with a ring. And the ring structure, that was how the addition came. It was coming from the direct sum of vector spaces. The multiplication of these isomorphism classes in the Grothendieck ring, it corresponds to the tensor operation. So the product in K0 coming from the tensor product operation. So that's what we're going to be doing. We're going to be taking Grothendieck rings of monoidal categories. It's quite a sort of fancy setup, and I'm not doing a terribly good job of giving you that. But what I'm interested in is how do you do this magic step from going from the natural numbers or the integers to finding this higher structure, finite dimensional vector spaces, whose K0, when you decategorify, gives you the ring you started with. And I claim when you've done that, you've actually, because you sort of added an extra layer. You don't just have objects, you've added an extra layer of these maps between objects. And you sort of found some sort of higher structure underlying the natural numbers in passing from n to vector spaces. It's a sort of weird philosophy, but that's the game that I'm in, this categorification. So that was example. Yeah, so I didn't really do a very honest job. You don't just take isomorphism classes. You take the set of isomorphism classes, that's a monoid with an addition, and then you have to take the group completion of that. So just like the way you build Z from N by adjoining minuses, and it's the same in the K0 construction. You know, we want to have a ring at the end, so we've got to negate things. But it's a formal construction, and yeah, you saw that was why. My first example, I was going to the natural numbers, but when I wrote down what K0 of X was, it was actually Z. It's kind of you add in minuses. Okay, so that was example 0 vector spaces, which was a pretty lame example. I'm going to give you example 1, which will bring us back to the story of symmetric functions that I was telling earlier. So example 1 is due to Frobenius and Schur. So this was sort of at the birth of the subject of representation theory, roughly 1900. And what they did is they took this ring of symmetric functions, which in 1900 was one of the staples. They all knew their symmetric function identities. They all knew their Newton identities and their elementary symmetric polynomials. Although, of course, they didn't know they were categorifying this ring because they didn't have that language in any way at all, what they did is they found a category whose Grothendieck ring, K0, recovers the ring of symmetric functions. I'm going to try and give you a kind of a glimpse of this story without giving too many technical details. So I need to introduce the symmetric group Sn. So this is a group, it's the group of all permutations of the set 1 through n. And you can take 2 permutations and you can compose them. You can do one after the other, and that gives you an operation on permutations, making the set Sn of all such permutations into a group. So look, here I've given a permutation of 1, 2, 3, 4, map 1 to 2, 2 to 3, 3 to 4, 4 to 1. I like to draw that permutation as a string diagram. You see what I've got there? My functions sort of go from bottom to top. So these are the numbers 1, 2, 3, 4. And this permutation, which maps 1 to 2, I indicate it by just joining 1 at the bottom to 2 at the top. And then that string is 2 going to 3, 3 going to 4, 4 going to 1. Right? So that I kind of like these string diagrams to represent permutations. Suddenly I'm starting to draw pictures. So I'm trying to tell quite a complicated story at this point. So I'm going to, it's fine, just trying to give the general sense of what it is that I'm doing, what this categorification is, why it's kind of remarkable. I've got this symmetric group Sn, this group of all permutations. There are n factorial of them. Actually, I need everything to be linear over a field. So I'm going to pass from the set Sn to what's called the group algebra, Rsn. So it's just the real vector space spanned by those permutations, and then you extend the multiplication operation linearly to make this actually into a ring, in fact, into an R algebra. And then I take that R algebra, instead of VEC that we had before, I'm going to take the algebra RSN and pass to its Grothendieck group, K0 of RSN. And I'm not quite telling you enough. I didn't tell you enough before either. But you can think of this K0 RSN in really a very elementary way. I think it's not how we're taught in as undergraduate math students. We're taught to think about the category of finite-dimensional RSN modules these days. But you can actually say what the Grothendieck group is in very elementary terms. The elements of the Grothendieck group, they're isomorphism classes of idempotents. What's an idempotent? An idempotent is a square matrix, maybe a 5 by 5 matrix, whose elements are these elements of this group algebra, so linear combinations of permutations. And idempotent means that when you take that matrix and you square it using the multiplication of matrix rule, plus you know how to multiply in the group algebra Sn, a squared equals a. That makes that matrix an idempotent. And the Grothendieck group you can just think of as being isomorphism classes of these matrix idempotents. I need to tell you what does it mean for two of these matrix idempotents to be isomorphic. So they're both square matrices, but they might be square matrices of different sizes. They're said to be isomorphic if you can find some more matrices x and y, which won't be square, so that A is x times y and B is y times x. And that gives an equivalence relation on these matrix idempotents. And the Grothendieck ring K0RSN is exactly that set of equivalence classes. Well, you have to take the group completion of it to add minuses as well as pluses. I haven't told you what addition is. So addition is right here. If A is a 5 by 5 matrix idempotent and B is a 7 by 7 matrix idempotent, you can take the direct sum of those matrices. You just build that block diagonal matrix. And that's the operation on idempotents. If A and B squared to themselves, this block diagonal matrix squares to itself. That's the operation on these idempotents that gives you the addition in the Grothendieck group, this K0RSN that I told you. So the famous theorem of Frobenius and Schur from 1900, they say that actually, if you take all of these Grothendieck groups, for all symmetric groups, for all n greater than or equal to 0, S0, S1, S2, and so on, and you put them all together to get that great big direct sum of abelian groups, that abelian group is actually isomorphic to the ring of symmetric functions. But that's a ring, so's the left-hand side. There's a natural tensor product operation on the left-hand side, which I'm trying to tell you down here. You can take two of these matrix idempotents and you can tensor them together to get another matrix. That makes these idempotents actually into a monoidal category. I'm going to do a slight, so I'm telling you when A is a 1 by 1 matrix, and B is a 1 by 1 matrix. That just means A is an element of the group algebra of Sn, B is an element of the group algebra of Sm, and A squared equals A, B squared is B. So, there's sort of my picture of A. It's like some permutation with n strings. And B is some permutation with m strings. And you do this stupid thing. You take the string diagram for A, and you just stick it to the left of the string diagram for B. And that gives you a bigger string diagram for a permutation in the symmetric group Sn plus m. And that's how those 1 by 1 matrix idempotents tensor together. That's the monoidal product on these RSN modules, which I'm trying to describe in terms of idempotents. And when you have matrices, well, you have to use the Kronecker product of matrices to boil it down to the operation I just explained. So that's this amazing thing, K0RSN. That tensor operation makes that into a ring. And Frobenius and Schur already in 1900 knew that this was the ring of symmetric functions. So under their isomorphism, right? So under this isomorphism that Frobenius and Schur worked out, literally the first theorem in representation theory, this was, they showed that inside lambda, the elementary symmetric function En, that nth elementary symmetric function, it corresponds to some matrix idempotent. In fact, it's a 1 by 1 matrix idempotent That's En, right? And then remember these square brackets, that was taking isomorphism class. And what is En? I've written it out here. You sum over all elements of Sn, that's the permutation. You put the sign of the permutation, and then you divide by n factorial. And many of you know that's the idempotent corresponding to the sign representation of the symmetric of Sn. So in the Grothendieck ring, the isomorphism class of the sign representation for Sn corresponds to the nth elementary symmetric function under that Frobenius-Schur isomorphism. In fact, the primitive idempotents in these RSNs, the idempotents that you can't split as sums of two orthogonal idempotents, the kind of basic ones, on this side, they exactly go over to these Schur functions, these S lambdas, which was my favorite basis for the ring of symmetric functions. Those things that were labeled by partitions. So those partitions become labeling primitive idempotents. And in fact, that's why these are called Schur functions. And Schur was exactly thinking about these idempotents in group algebras of symmetric groups to kind of realize this remarkable basis and this remarkable inner product on symmetric functions. If you take two Schur functions and you multiply them together in the ring of symmetric functions, you can write it as a linear combination of Schur functions. And amazingly, all the coefficients are positive natural numbers. That's explained by this theory, by the fact that Schur and Frobenius categorified symmetric functions. Categorification explains that sort of positivity. So that's kind of that was sort of the first motivation for categorifying things. The positivity of the structure constants, they're called Littlewood-Richardson coefficients for these Schur functions. Once you've categorified lambda, it follows immediately because you're actually tensoring some vector spaces together and you're counting dimensions. So that, that's kind of a nice way to see it. Multiplying by E1, that's inducing from Sn to Sn plus 1. And multiplying by E1 star is the adjoint of inducing, that's restricting. So this is sort of this classical theory with 1900. So then I've got one more example. I have just enough time because I've gone back in time. I haven't gone forward in time. But it's kind of amazing for me that in 1900, maybe 1904 was when Schur kind of finished off that story. They had categorified this ring of symmetric functions using the representation theory of symmetric groups. And they had this incredibly rich, beautiful story. They didn't have the modern language to say it. They certainly didn't use the word categorification or monoidal category or even idempotents probably at that time. But my second example is we've got a leap from 1900 to 2008. I find it shocking that the last thing I'm telling you about was only done recently because it clearly have been done in the 1950s and probably should have been done in the 1950s. But somehow we didn't have, it wasn't me, but some vision was lacking at that point. And it was, so I'm finally telling you this story. It was introduced by Khovanov in literally it's 2008. Remember, I had the Heisenberg ring acting on the ring of symmetric functions. I've told you how the ring of symmetric functions gets categorified by looking at this Grothendieck ring coming from representations of symmetric groups. What Khovanov did was he explained how to categorify the entire Heisenberg ring, actually in its action on symmetric functions. And this is finally the Heisenberg category. So this is Khovanov's category, which categorifies the Heisenberg ring. So I denote it just by Heis. That's Khovanov's Heisenberg category. And I want to give you just the flavor very quickly, but so the formal language, this is an R-linear monoidal category. When you take its Grothendieck ring, it's a monoidal category, so it's not Grothendieck group, it's Grothendieck ring. When you take its Grothendieck ring, the theorem I'm going to tell you in the next slide is that you exactly get this Heisenberg ring H. But let me try and give you just a glimpse of what the Heisenberg category is. So it's a category. it's a monoidal category. So it's a category with a tensor product on it. I'm going to actually draw it. It's going to be done with string diagrams. So like for the symmetric group, the tensor product is just going to be taking two string diagrams and sticking them side by side. So I need objects and I need morphisms. Well, the objects are just sequences of ups and downs. Up, up, down, down, up. Some finite sequence of ups and downs. That's an object in the Heisenberg category. And then a morphism in the Heisenberg category, well, it's going to be a vector space. And I need to give you some vectors that you take R linear combinations of. So I've drawn a typical morphism here, right? So this is a morphism from up, up, down, up, up to up, 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 down, up. And you just draw some strings. They've got to be oriented strings because there's arrows. So you have to draw strings that the arrows give an orientation on. And then there's some crossings, and then there's some dots. In fact, the sort of string diagrams that you get for morphisms in the Heisenberg category, you basically start from these very simple generating morphisms, the up dot, the up crossing, and then this is the right cap and the right cut. And then you can compose these vertically and horizontally, and you build a big string diagram like this. It's sort of built from gluing together vertically and horizontally all of these smaller diagrams. So working in a monoidal category, you're suddenly doing two-dimensional algebra where you're gluing horizontally and vertically. It's very natural to be doing diagrams when you're categorifying. So these diagrams, well, they look much like diagrams for permutations. Remember my permutation diagrams, it was just strings, and there were no cups and caps and no dots and no arrows on the strings, but it's very similar flavor. It's just we've got kind of more complicated diagrams in H, the thing that categorifies H compared to the thing that categorified lambda. Okay, so the story will be fairly quick now. So I gave you these generating morphisms, this up dot, up crossing, and these cups and caps. They have to satisfy some relations. So I've just drawn the string diagrams. These are the usual relations for the symmetric group, actually, the crossing squares to the identity, and this is the braid relation. And then these cups and caps, they have to satisfy those two identities, which are called the zigzag identities. So suddenly this diagrammatic calculus starts to become very convenient. And there's one relation involving the dot. When you slide the dot past the crossing, you get the identity, these two vertical strings. I call that the de Maizière relation. That's a bit mysterious why that's there. And then the most important relation of all is that this guy here, this is a 1/2 matrix of morphisms in the Heisenberg category. This 1/2 matrix has to have a two-sided inverse. Well, that two-sided inverse will be a 2/1 matrix, right? So that when you compose those matrices both ways around, you get the appropriate 1/1 or 2/2 identity matrix. And actually the entries of that inverse, they give you a leftward crossing and a leftward cap. And just in case you want a leftward cup, that's why the dot is there. You kind of need the dot in order to define an appropriate diagram that's this leftward cap. And then you can start drawing these diagrams. It looks like kind of maybe the diagram of a knot or a link or something. And this category is so beautiful that these diagrams have complete planar isotopy. So you can slide these diagrams around and it doesn't change the morphism that they represent in the Heisenberg category. So it's a bit of a strange relation. This 1/2 matrix is invertible. And I think I might be just about at the end. Khovanov introduced this category. And of course, he introduced it because he was expecting that the Grothendieck ring of his category, K0 highs, should be isomorphic to the Heisenberg ring, this very classical integer version of the infinite dimensional Heisenberg Lie algebra. And he nearly proved it, but he didn't quite. And so the final step in the proof, building on all his ideas, was something that we contributed. And it was only, I guess it was already 2019 now, but it wasn't so long ago. And so how it goes is that there's an object that's this up arrow in the Heisenberg category. Its isomorphism class corresponds to the generator E1 of the Heisenberg ring. And the down arrow corresponds to E1 star in the Heisenberg ring. Remember, these up arrows and down arrows, E1 multiplying by E1 or E1 star, they were induction or restriction. between representations of symmetric groups. And these diagrams are really kind of pictorial ways of calculating with induction and restriction in this story. This matrix, look, this weird matrix, why should that be invertible? Well, that matrix, that's a morphism from the object up, tensor down, up, down, to the object down. Remember, my morphisms go up. So that entry is and this guy is going from the empty string diagram, that's the monoidal identity in this monoidal category, from there to down, up. So this matrix, it's a morphism from the direct sum, up, down, direct sum, the unit, to down, up. When you take isomorphism class, so you pass to the Grothendieck ring, up becomes E1, down becomes E1 star, the monoidal unit becomes the one in that ring, and this is the other way around, so it's E1 star, E1. What this weird relation about this matrix being invertible is saying is that these objects are isomorphic. That means that they become equal when you take K0. So it gives you this relation, E1, E1 star plus 1 is E1 star, E1 in the Grothendieck ring, which is exactly that silliest first Heisenberg relation. Kind of one of the magic things about this story is that you only need to get that very first Heisenberg relation involving E1 right, with this one silly 1×2 matrix being invertible, and you get all the other ones by the magic of idempotence, by this magic of Grothendieck ring. So I think I think I've got one more page, but kind of I hope I've tried to give you this idea that you can draw a permutation as a string diagram. In Khovanov's Heisenberg category, it's generalizing those string diagrams of permutations to this more general family of string diagrams where you have ups and downs, and these dots, they play kind of a slightly complicated role. I haven't begun to explain why they're needed. But what he came up with is this incredibly clean and very elegant, beautiful object, this Heisenberg category, which I haven't done a very good job of telling you what it is. It's sort of symmetric groups together with adjunctions built in. So the symmetric groups, you already saw the ERs, and these down strings let you see the ER stars. And to me, it's kind of amazing that such a natural classical topic, this Heisenberg ring action on symmetric functions, it took 108 years before somebody thought it should be categorified. And that's what Heisenberg, what Khovanov did for us. So this is my last page. There's actually a family of Heisenberg categories, one for each integer, each C and Z, and I call that C central charge. And Khovanov's one is the one of central charge -1. We saw that -1 coming in our box space representation. But in fact, there's a family of them for every central charge in the Heisenberg category. And they have very many common properties. So you study them all in a uniform way. And whereas Heisenberg -1 acts on representations of symmetric groups by induction and restriction, Heisenberg 0, which is my personal favorite, it's actually a little bit simpler in some ways. It acts on representations of the general linear group in a very nice way. So this Heisenberg category, I haven't really sold it very well, but it somehow gives a higher structure behind representation theory of these sorts of classical groups like symmetric groups and general linear groups. And so what we've actually built, we've built a sort of a general structure theory for what we call, well, when you have a monoidal category, monoidal categories act on module categories. When you have a Heisenberg module category, all of these like representations of symmetrical general linear groups, they're all examples. We've built this nice, very clean, elegant structure theory for studying them all in a uniform way. So it's a sort of higher representation theory way of unifying lots and lots of classical representation theory about these groups. So it's kind of honestly a worthwhile step. Khovanov's idea of introducing this category, it turns out to actually give a wonderful unification of lots of old topics where it was all a bit piecemeal before. So that's my attempt to explain what I do. Thank you very much.
Does anyone in the room first have any questions for Jon? Oh, can you use the microphone? Sorry. I guess there's people online that can't hear you otherwise.
Can you say a bit more about where the zero shows up, please?
About
Where the zero in Heisenberg zero? Like,
yeah,
I'm guessing you.
so I haven't set up the language of monoidal categories or modular categories very well, but Heisenberg -1 acts on representations of symmetric groups, and the up arrow acts as a functor. It's the induction functor, and the down arrow acts as the restriction functor. For Heisenberg 0, it acts on representations of the general linear group. And in that case, the up arrow acts as tensoring with the natural module, and the down arrow acts with tensoring with the dual of the natural module. And tensoring with the natural module and its dual, V tensor V star is isomorphic to V star tensor V. So up down and down up in that action they're just isomorphic. So this commutator of what was called E1 and E1 star, in that case, they just commute. So that's why there's a zero there. It's sort of like the Z, the central charge is zero in that case. So it's a sort of degenerate from the Heisenberg point of view, but from this structure theory, it's just as interesting.
Related to that question, can you say anything about what the other classical categories, the other highs see?
So you like these Ariki-Koike algebras. They are my favorite example too, actually. For them, you need to a little bit tweak this Heisenberg category, because my crossing was drawn as a singular crossing. You need to have a kind of over-under crossing, like in knot theory, because you have to build in the braiding of the Hecke algebra underlying those Ariki-Koike algebras. But those are examples. So modules over those are module categories, not over this Heisenberg, but of a slight variation of it, where you've deformed the braiding a little bit. That's a nice example.
Get other like other matrix groups coming up, like GLN? Do you get orthogonal groups, or do you get other kind of diagrams?
That's what we're sort of working on now. We didn't set this up, but the story I've told with these Heisenberg categories, this is sort of the vanilla flavor story, which is related to symmetric and general linear groups. But in fact, there's such a story for every family of classical group. So this was the story for the general linear family. There's a story for the orthosymplectic family. I put that in the same family because for me, orthogonal and symplectic are all just together as the orthosymplectic super algebra. So you kind of put symplectic and orthogonal together. And then there are two other families of classical supergroups, the PN and the QN families. And in each of them, there's an analogous story. There's a version of Khovanov's Heisenberg category in each of those four families. And they're different, but the kind of methods that you use are very parallel in those settings. And so if you're doing it for OSP, you're doing some sort of Brouwer category sort of stuff, and it's not built yet, but we're building this theory, and it'll give a similar unified way of approaching all representation theory of those classical groups.
So where symmetric functions came up here, you get odd symmetric functions for either P or PN or QN or something?
Yeah, I use all sorts of symmetric functions are everywhere, of course, and different sorts of symmetric functions are showing up. Often these Schur-Q functions play a role.
Thank you.
So speaking of knots, in low-dimensional topology, we have some categorifications where decategorification typically means taking the Euler characteristic with respect to some grading. Is there an easy way of explaining how that comes into the picture? Like the Euler characteristic, that alternating sign pattern?
Yeah, so I mean, at the level I was speaking, I was explaining how when I gave my silly vector space example, how taking dimension was a way to take a vector space and get a natural number. Actually, I should have said take a complex of vector spaces and take the alternating sum of the dimensions, so take the Euler characteristic of that complex, and then you actually get an integer, not just a positive integer. So with that very silly example, 0 level, if you're trying to categorify the idea of taking negative, you naturally start thinking about chain complexes. And of course, this was you know Khovanov's story. So he didn't do the Heisenberg category in 2008. Before then, he'd come up with this wonderful family of link invariants known as Khovanov homology, which categorify Jones polynomial. And so he constructed this chain complex where each homology group is a link invariant. And when you kind of decategorify Khovanov homology, taking this Euler characteristic, you recover this somewhat, well, I can't call it a classical link invariant because already Jones was in the 1980s and it was already quantum groups were everywhere there. But and then I think this Khovanov came to this Heisenberg stuff more as a sort of a sport. It was like a little hobby. He'd had these big successes of categorifying link invariants, and he was trying to just apply the same kind of not theory, diagrammatic inspired philosophy and looking at some classical topics. And this is the most classical topic in representation theory. And it's kind of shocking that he came up with this new approach, this new Heisenberg category that people should have done it before, but he had this new vision.
Right. So I mean, I've seen the Khovanov homology. I'm a little bit familiar with that. I was just think about something very basic, such as why the alternating sum? Like when you take decategorify a complex of vector spaces, why do you take an alternating sum of the dimensions? Why is that natural?
Yeah, that's. I mean, there's obviously a long history to that idea. I don't really have a good answer.
Right. Yeah. Thanks.
Euler characteristic has lovely properties with respect to constructions that you make.
Right. Thank you.
Okay. If there are no further questions and none online, I assume, then let's thank Jon again.